Okay, so I hope you've all had a think about what some of the issues might be. So here are some potential problems I think with the regular expression-based approach here. So first one, and probably quite an important one, it's a complete pain in the bottom having to do this because actually it turns out there are huge numbers of potential combinations of pos tags that could form definite noun phrases. So you need to come up with rules that would make sure that you capture all of those combinations. And just to add a little bit of salt to the wound, some of the rules that you write may also find things that aren't definite noun phrases, as well as ones that are. So you'll get false positives as well as false negatives. So you've got a real issue there of making sure that you're only picking up definite noun phrases and that your rules are wide enough that they can pick up all the different combinations, but also not so wide that they also pick up stuff that isn't a definite noun phrase. It's an absolute nightmare. If you don't believe me, or you just fancy a bit more of this fun or pain, then pip install NLTK, that stands for the Natural Language Toolkit. Then write a program with the following code or enter these commands sequentially in your console. Either works fine. So import NLTK and then run nltk.app.chunkparser. And that's a little app that is within the Natural Language Toolkit that allows you to write regular expression rules that will correctly try to correctly chunk into subconstituents sentences, and you can test it on hundreds of examples, and it will keep an eye on the percentage that you've identified and the percentage you incorrectly identified with each iteration. There are instructions in the app that sort of guide you through it more. Have a go, but I warn you, it will drive you insane because there are. You will notice your success going up and down quite a lot, and you will come across very quickly this problem that you are. It's very difficult to find solid rules that only pick up noun phrases and reliably pick up a good percentage of noun phrases, definite noun phrases as well. There's also another problem though. So let's imagine the whole reason we're doing this is that we're looking for named entities in some free text, right? So let's not forget why we're doing this. So let's think about maybe a typical example. Let's say we want to look for some named entities in some notes made by paramedics at the scene of an incident. Free text data, we want to grab out the named entities for various analytical purposes. So, which of these do you think is a more realistic reflection of the kind of notes you'd expect to see in the paramedic crew notes? A. It was morning and a slight chill was in the air. I arrived to find that Mrs. Smith had clearly taken an unpleasant fall and was in need of help. Quickly, and without a moment's thought, I rushed to her and asked if she was in any pain. Or might we expect to see something more like this? Arrived AM. Mrs. Smith had fallen. Rapid assistance given. Asked if she was in pain. And clearly, I think we can all agree that the second of those is more likely. Now, that's not to say that our wonderful paramedics are not accomplished wordsmiths, but realistically, in those kind of situations, and indeed in most situations, most of us would not write imperfect grammar. It simply doesn't happen. And particularly in a high pressure situation like that, that's not going to happen. The problem is the regular expression based approach of setting up regular expression based rules that allow us to try and find the particular patterns, syntactic patterns that form definite noun phrases so we can identify named entities. They necessarily assume that the text is going to be at least written consistently, and ideally in perfect grammar. And so, if it's not perfect grammar, the imperfect grammar that it's written in will need to be consistent amongst all your text, and that's clearly not going to happen. So it's a massive problem when we try to apply this to the real world. So clearly, that's not going to be a great help to us. So is there an alternative solution, a better solution? Well, it turns out there is. And it doesn't rely on having to use grammatical rules and therefore necessarily assuming that the text is written in those grammatical rules. And doesn't mean that we have to find all of these different rules that may also find things that aren't noun phrases, etc., etc. And that alternative is called SpaCy. And SpaCy is a Python library for natural language processing that includes lots and lots of stuff, but amongst many other things, some AI-based methods for named entity recognition that are really, really useful. So SpaCy's become a very well-regarded and very widely used Python library that does make these kinds of natural language processing tasks, particularly parsing-based tasks such as named entity recognition, really easy. And I mean really easy. The one bit of code you're going to be doing today, you're going to see how easy this is to use. So if you haven't already, to install SpaCy, you just use pip. So pip install SpaCy from your command prompt or terminal. And I've put the link there to the SpaCy website. There's some really good information on there, really good tutorials, and lots of information if you start using SpaCy in earnest about all of the different things that you can do with it. So I'd recommend, if you sort of get on with SpaCy and you're interested in natural language processing, to check it out, because there are huge amounts of stuff that you can actually do with this thing. So obviously the thing we're interested in at the moment for using SpaCy is for named entity recognition. So let's talk a little bit about how SpaCy works for named entity recognition that's different to the approach that we were trying to use before. So obviously before we were trying to use regular expression-based rules to specify search patterns of types of pos tag and sequences of pos tag that we would expect to see to find definite noun phrases. Rather than any of that, what SpaCy does is it uses an AI machine learning based approach to basically predict whether a particular word or a group of words based on that word and the pos tag of the word or words itself, and the words and their associated pos tags that come before and after it, whether they are, based on all that information, whether that is a named entity or not. So it's not just, so basically it's looking at a word and what pos tag it is, and then it's looking at the words that come before it, and it's looking at the words that come after it, and their associated pos tags. It even looks at the punctuation, and based on that information, it's then making a prediction about whether, given that kind of pattern of things that it's seeing before and after and the word itself, whether it thinks that this is likely to be a noun phrase. And it does that in the same way as any machine learning, by learning based on prior learning based on lots and lots of data, where it's learned the kinds of patterns. So rather than us, this is the beauty of machine learning, rather than us as humans trying to specify all of these rules and try and work out what they all might be, we essentially get the machine to look for all of those really complex to find and hidden and difficult rules that underlie these texts, so that we can then use that knowledge to then predict based on new data. So all its previous learning is on corpuses, which are collections of written text, where it's basically learned the syntactic patterns that it expects to see when a named entity is present. And these corpuses are huge, generally. They're very large-scale volumes of text, so it gets to see lots of text and how text is formed, and not just in beautiful grammar as well, the way people are actually writing. So specifically, SpaCy learns using something called a convolutional neural network. Now, I'm keeping this light, so we're not going to go into detail about what a convolutional neural network is at this stage. I will just give you a brief reminder. I think Mike earlier in the course on the machine learning talked a little bit about neural networks, but again, didn't go into huge amounts of detail, and I'm not going to either. This is really just to give you a very basic understanding, a reminder of what a neural network does. So neural networks are basically set up to emulate the way in which brain works, which is basically the idea of having neurons which are connected by synapses with signals being sent along the synapses to the neurons. Now, neural networks have multiple layers of nodes which emulate the neurons, and connections between these nodes on different layers which emulate the synapses, with inputs to and outputs from each of the nodes being sent as signals to the other node. And each signal has each connection, has a weight associated with it. So you may have a particular connection where the weighting is twice the amount of a connection elsewhere in the network, for example. So twice the amount will come through that connection in terms of the value that's being fed through. That all sounds very abstract. It is very abstract, actually, in a lot of ways. So this is basically, I think Mike showed you the website for this, where you can sort of play around with a neural network and get an idea about what they're doing. But basically, you've got some inputs that go into an input layer, and some outputs, one or more outputs which go into an output layer, and basically numbers get fed through this thing, and they get fed along to the different nodes, and they're connected. The different nodes and different layers are connected by the connections, and there's different weights that are applied to the values that are coming in and going out, and there were different functions. So you might have a layer, just give a really simple example, where all of the numbers that come in get added up, and then that becomes the output. That'd be a really simple example. But you may have more complex functions, but it's that each one will perform some sort of function that takes an input that will be weighted according to the way it came in, and will chuck out an output based on those inputs. And so what you end up trying to do is to try to get to a situation so where you're training a neural network, what you're essentially trying to do is to say, okay, well, given these inputs, this is the output that you would expect to see. So this is what I want you as a neural network to learn. So let's say the inputs are, 1 and 2, and the output is 5. Then we need the neural network to adjust itself, to adjust the weights, adjust the way in which it connects to things, adjust the functions, so that given an input of 1 and 2, it will come to an answer of 5. And it may be doing it will be doing all sorts of abstract stuff. And this is one of the ironies of neural networks, that they were first designed to learn, so we'd learn more about how the human brain actually works. And the irony is that they've now become so complicated that they're incredibly useful, but they're what we call black box. And that means we don't really understand how they're working and how they're coming to the learning that to transform these inputs into that output. So, and there may be all sorts of stuff that just doesn't make sense, but it works. Basically, that's the sort of basic concept of neural networks. If you are interested, there's huge amounts of literature out there around neural networks, and any of the team will be happy to talk to you, particularly Mike and Tom. So in SpaCy, the inputs to our neural network are the pos-tagged groups of words within a corpus. This word, which is a determiner, this word, which is a noun, etc. And those pos-tagged groups of words are converted to numbers, because computers have to deal in numbers, and so therefore a neural network has to work with numbers. And we'll come on to how that's done in a bit. And basically it's trying to adjust its weights and internal functions so that when it's told, for example, that word 3 in the group of words that it's been given is a named entity, and so that's an output of 1 for named entity and maybe 0 for not a named entity, it's able to come up with the same output based on the tags of word 3, which is the named entity, word 2, the word before it, word 4, the word after it, word 1, 2 words before it, etc. So it's got to do something with those, in this case, 5 numbers within that network, so that the answer comes out as 1. And that, of course, is easy if it was just one example, but then it needs to be able to consistently then apply those rules so that the same way it configures itself will also, when it's given another 5 inputs that should come out with an output of 0, that it comes to that as well. So this all sounds very complicated. Don't worry too much about this. I just want to give you a sense about how this is doing. But essentially, the key takeaway message here is that SpaCy predicts whether a word or group of words represent a named entity based on prior learning from huge amounts of text in these corpuses, where it's learned the kinds of syntactic patterns that tend to surround named entities, and it's using that prior learning in order to judge whether a named entity is there or not. So now know a little bit broadly how it works. Let's try it out. So as I say, make sure you've installed SpaCy using pip install SpaCy. And if you haven't already, make sure you've downloaded the NCore Web SM model. That might take a little while, so do feel free to pause the video whilst you do that. And Python M SpaCy download NCore Web SM, that needs to go in to your command prompt if you're using Windows or Terminal if you're using Linux. And what that is it's one of the pre-trained learning models. We just said it was SpaCy sort of pre-trained on huge volumes of text. There's actually lots of core pre-trained models that SpaCy has. Most of the distinctions between the pre-trained models are the language. So the EN stands for English. Core being one of the core models, which has been basically had its learning developed on a very wide variety of text. And the SM at the end indicates that it's the small version. There's also a medium, which is MD, and large LG versions of the this model as well. But we're just going to use the small one for now. So this is the pre-trained stuff. So we don't have to worry at this stage about training up our model. We can just use this pre-trained model that's already seen lots and lots of text. We'll use the small version of it to see if it's enough for our purposes, and we'll apply that to our problem. So you've all been provided with a file called trumparticle.txt. This is text from a New York Times news article about the firing of an FBI agent. So what we're going to do is we're going to use SpaCy to extract the named entities and their predicted classification. So not just that this is a named entity, but what type it is. So Trump is a name, for example, from this news story in this file. So what I want you to do is start a new .py file, and wherever you save it, make sure that the trumparticle.txt file is in the same location. So once you've done that, I'm now going to show you the code. This is the entire code to actually get named entity recognition using SpaCy on our Trump article file. So before you copy any of this down, I just want to talk you through it so you can understand what's actually happening. And if you ignore the comments, you'll see that there are very few lines of code. In fact, we've got 9 lines of code here, of non-comment code. And actually, most of that is just prep and some of the stuff that you do after. So the first thing we do, as you have been drummed into by now, is we need to import the libraries we need. So in this case, we need SpaCy, so we're going to import SpaCy. And we're also going to import the NCore WebSM class. That's the model that we downloaded, and that's treated, remember, from your object-oriented training, this is treated essentially as an object here. First thing we're going to do is load this model into a variable that we're going to call NLP, natural language processing. So we just say NLP equals NCore WebSM .load. And that will automatically load that model in. So now we can just refer to NLP to do everything we need to do with that model. So then what we want to do is to read in the document within which we're going to look for named entities. So in this case, that's our trumparticle.txt. Again, you'll likely be familiar with this from your sort of file reading and writing. But all we're going to do here is open up the file, and we're going to do a whole read of the whole thing at once, and just dump it into this variable we call raw read. The only thing we are going to do is to use the dot strip um, function in order to remove any spaces at the start and end of the file. So just strip out any sort of leading and leading white space, and the same at the end as well. So that's all that function's doing, and we're using the with command here. Remember, that keeps the file open for as long as we are doing the things within the indentation, and then the file is automatically closed once that's been done. So now we've loaded up the model that we're going to use, the pre-trained SpaCy model, and we've loaded the text file that we want to analyze into a variable called raw read. This next line of code does all of the magic for you. So I'm storing the results in something called article. This is standard nomenclature when dealing with SpaCy, that they call the outputs to the model articles. So I've just called it article equals NLP, which, remember, is the model we've loaded in, our core model in this case, and the only input I'm giving to that is raw read. In other words, the raw dump of the text that I want to look for, that I want to parse and look for named entities. So that single line will do everything you need it to. So then we just need to pull out the named entities. And the beauty of SpaCy is it's got this functionality built into it. So what we want to do here is to store the named entity categories, which are referred to as labels. So those are the things, remember, like person, org, geopolitical entity, that sort of thing. They're the labels. We want to store those in a list. So we're using list comprehension here, which you probably remember from earlier in the course. So I'm going to call my list labels. And basically what that's saying is, so the named entity categories are stored within a label, within the ents subclass of the article, which is in itself the output from the model output, the SpaCy model output. So what we're saying is go through. Ent stands for entities here, by the way. So for grab me the label for each entity in within the article. That's basically what that's saying, and the label will be the type of named entity, the category. And then so we now got a list of all the labels. So now what I'm going to do is just simply print each named entity along with the its corresponding label, the predicted category. So I've just got a simple for loop here to loop through the length of article.ents, which is a list. So the list of entities which has been identified, the predictions from the model, and I'm just going to get it to print each article entity, which will be the named entity itself. I've put followed by a colon, and then the corresponding label, which I've stored in a label. So grab me the first entity, so the first one in the article.ents list, and its corresponding label that I've stored in the labels list. And that's all that's doing. So it's just grabbing the named entity and its corresponding label and printing them to screen. So what I want you to do now is to type out that code, make sure that you're understanding what it's doing, have a read of the comments as well, just to make sure that you fully understand what that's doing, and then run it and see what happens. So do that. Once you've done that, then move on to the next video.